Greetings. This is the review for our first midterm. It occurs in week 5. The midterms and the final are all in class and done the same way. All tests are closed book and closed notes. We'll give you scratch paper if you need to. I'll also include an equation sheet, which will actually be the equations that we talk about here that are provided that you'll have seen if you looked at previous tests. Bring a calculator, no super smart calculators with documents on them, just so we have a fair playing field. And each of the tests are on Monday and Wednesday and Friday of the 5th week, 8 till 8:30 nominally. Probably it will start 5 minutes earlier, and you'll have perhaps a minute to clear up if you need it as we close the test. The material is the stuff in the first part of the class from 1.1 through to 4.1. You've been in those classes, so you've seen what it is. But specifically, just to make life a little easier for you, the specific topics or questions in this midterm. The first one is on viscosity, which is week 1, Wednesday and Friday lectures. I guess it was offset this year, so it's not the same, but those topics. The Wednesday is pressure on planar surfaces, and the Friday is accelerating fluids. And so I will review the material specifically that goes into the test, and you can check prior tests to also see that the review sessions have been congruent with the material on the test. So I'm pretty sure that if you look at the material that we'll talk about today, you'll have everything you need to be able to successfully complete the test. So given that we're restricted to those certain topics, the first one comes under the week 1 topics of fluid properties. Newton's law of viscosity links the shear stress to the rate of change of velocity across a shearing fluid divided by the length over which that occurs, and it defines a coefficient, which is the dynamic viscosity, which is in units of Pascal seconds. We deal only with Newtonian fluids where the shear stress is directly proportional to the shearing rate, dVx dy, and not Bingham fluids where there's some shear stress that needs to be initiated before it flows. We think of the fluid as filling in a small gap, shearing a top plate on top of a lower plate, shearing it either at a velocity in the x direction or applying a shear stress to give that velocity in the x direction, or getting a force, which is just a force divided by area gives us shear stress. And I guess the things to note is that we assume that there's a linear distribution of velocities from being fixed at the lower plate to a maximum velocity at the top, and it varies linearly between that, so that dVx dy is constant through this gap. And I guess the other thing that it's important to know is that on any plane that you cut through it, the shear stress that's acting on that plane is exactly the same as the shear stress that's acting on the top. And so you can evaluate the magnitudes of the shear forces to be able to typically deal with some kind of free body diagram that's including a force as some component of that. We talked about fluid pressures at a point. We know that the important equations are that one that's always true is that pressure changes with elevation and is equal to the unit weight of the fluid, which is the density times gravity. We know that this is always true. We know that there's a minus sign here because our sign convention is for z positive going upwards, and this gives us a value that is congruent for a positive value of a density and gravitational acceleration, which are both positive constants. And so this is just a matter to keep the dimensionality and the sign right on this. We know that if you go horizontally in a fluid, pressures don't change, and that's the second set of equations we use. We know that to get pressure at any location, we have to integrate these two expressions, this top expression actually, only the top expression, and depending on whether we have a gas, we get some variation of pressure with elevation, and if we have a liquid, which is constant density, then we end up with this simple expression. whereby the pressure at some point is equal to the pressure at some other location, typically a surface, plus the elevation change times the unit weight. It can be added or subtracted because h is a magnitude, a positive magnitude, and it matters whether you're going up or down. So you need to keep in mind this value. There is not a question on pressure changes at a location except in this particular test. So even though we talked about that, you don't need it. We talked about manometry. Manometry equations come directly from the previous stuff that we've talked about. If you go up, you subtract pressures. If you go down, you add pressures. If you're in a gas, the gas is 1,000 times less dense than a liquid, so you typically ignore the pressure changes that you have if you go up in elevation. And if you are in an evacuated component, you need the vapor pressure. If you're using the vapor pressure, you might be wanting to use your equations in absolute pressures as opposed to gauge pressures, because the ideal gas law is written in absolute pressures. There is not a manometry question on the test. There are, however, questions, viscosity we mentioned, but forces and pressures acting on structures. And so there are, I guess, three issues. One is that we can always get a resultant force that's acting on a surface by considering this diagram. The force is always given by the unit weight times the depth of the centroid vertically below the surface. So this coefficient here, these two terms are the average pressure that's acting on the surface. And actually this is the pressure that is acting at the centroid. So if you take the height of the free surface above that centroid, which is the balance point of the flat surface, then that gives you the pressure at this point. And this is just saying that the resultant force is given by the average pressure multiplied by the total area of this surface. And we have some standard results for that in terms of a width and a depth of, or a width and a height of a surface. And these are magnitudes where the centroid of this shape, or for any other shape, is defined in it. This is the portion that gives you the depth of the centroid below the surface of the water, and that gives you the resultant force that's acting perpendicular to the plate, but it doesn't act at that location, it acts at the center of pressure. And we can always get the center of pressure. The center of pressure will always be below the centroid for a liquid, which has unit weight. And we can get that location by defining y sub r. Y sub r is, importantly, the slope distance of that center of pressure from the surface. So this goes up along this axis, and it's divided into two components. It's the slope distance to the depth of the centroid, which is y sub c, plus a small amount, which is delta y sub c, which is given by this term. So this is the slope distance, this is the area of the plate, and this is the second moment of area around the x-axis of the centroid. And this is a standard result, and one of those standard results is just this for a rectangular plate, and we have talked about it also for a circle in class. And the reason that the point of action is below the centroid, so the centroid would be at half height here, right? This is h sub c, which is half. The reason that it's below the centroid is because the component due to the pressures acting at depth are larger than the ones acting closer to the surface. So these are just standard results. So you can get the force by using the centroid. You can get the point of action by using the slope distance to the centroid plus a small amount, which gives us y sub r. And then finally, we have to typically solve a problem by resolving moments about some, for want of a better term, failure mode. We talked about a gate in class, a circular gate, and took moments about the pivot point or the hinge of that gate. And we have to do that for solving these problems. That's the third part. So to do that, we need to know where the resultant acts, and we need to know how big that resultant is, and then we can typically resolve to be able to solve for the other components. We can always take moments We know that this distribution of pressures for a plate given here that is submerged some distance below a free surface would be a prism plus a triangle. If we want to get the location of where the resultant acts, we can always figure out what LR is just by taking moments where we know the magnitude of the force for the prism, the magnitude of the force for the triangular distribution, and the lever arms between those for the prismatic distribution and the triangular distribution. And that, if we do that, since we know that FR is equal to the sum of those two distributions, we can get the location of the resultant force. We can always do that. This is actually exactly the same as using this equation here. So it's probably may be easier for you to use this expression. Okay. So 3 things that you need to do for typically these forces on a plane. There is no buoyancy question, but you know that the reason that objects have buoyancy is because if you remove this little piece of fluid, the pressures acting upwards on this structure are less than the pressures acting downwards, and so there's a net buoyant force, and that buoyant force is equal to the volume of the empty structure multiplied by the surrounding liquid in this particular case. But you don't need that. And finally, the third item is for accelerating fluids. It is for linearly accelerating fluids. We know that the pressure differential with depth for linearly accelerating fluids is given by the density, gravitational acceleration, which always acts vertically, plus the acceleration in the z direction. We know that we work with a coordinate system, which is, in this case, y horizontally and z positive vertically. These are standard equations. So the pressure change in the vertical direction is this. If there's no acceleration in z, then it's just rho times g, which is our specific weight of the fluid. And this is the same as that expression we have. If it's accelerating in the horizontal direction at some acceleration in y, then the pressure changes according to this. And so we can use this to be able to calculate the change in pressure on the back of the sample if the system is closed by using each of these. And if the system is open, we can use those to look at the reorientation of the free surface of the fluid. The initial free surface, just from volume conservation constraints, right? It has to fit below this green line because this is the midpoint along mid-length of this tank. So that when it accelerates, the back elevation comes up, the forward elevation comes down. And we use this by defining a line which has 0 pressure on it and is no change of pressure as you go along it. And the standard solution for that is that the change in elevation of the free surface with length along this tank is given by this standard result. And this means that the gradient of this is composed of the portions that relate to accelerating horizontally, as in the case of the bus. Accelerating vertically would be if this is also going upwards. If it's not going upwards, then this term would not be there, be 0. And this allows us to get the orientation of this free surface, and we have to worry about fitting it into the same tank as it was before. This case on the left-hand side is if this is a closed tank that's full of water, and these would be the pressures that would be acting on the back surface that we could calculate by the magnitudes of the acceleration that we had, either by going up, in which case there'd be a pressure change along the tank, which would be augmented by some small amount because of an acceleration in the z direction. And if it's accelerating horizontally, then there would be also a pressure change in the y direction, which is controlled by the horizontal direction going from left to right. So it's important to realize whether the system is closed, in which case the free surface doesn't exist because it's filled up to the top, or if the system is open, in which case we have a free surface that can reorient itself, and therefore we can get the pressure distribution in this fluids as a result of this. Okay? So hopefully that will cover everything that you need. I'm pretty sure it does. This is exactly the equation sheet that you'll be given for the tests. Same equation sheet for all 3 tests on the Monday, Wednesday, and Friday. Okay? Good luck. Happy hunting.